All right, in this video, we're going to take a look at examples 6 and 7, where we will focus in on the cases of distinct and repeated irreducible quadratic factors. We talked about how to write down the generic form for such terms in the previous video, so you can check that out if you haven't done so already. All right, so starting with example 6, we've got our rational expression, and in the denominator we've got a linear factor, and we have a irreducible quadratic factor. So not repeated. Okay, so it's already factored for us, so that's good. So what we'll do is we'll just kind of pull this out of the integral itself. That's not needed. And we can write down the form. So copying this down, the linear factor contributes a form or a term of the form a over x minus 1, and the irreducible quadratic contributes a term of the form bx plus c. Okay. We talked about this in the previous video. Again, same procedure now. We just multiply by the entire denominator to clear all the fractions. So x squared minus 2x minus 1. And then here we have a times the irreducible quadratic plus, let's see, the irreducible quadratic cancels, and we have bx plus c times our linear factor, x minus 1. All right, I did promise when we began this section, partial fractions, that there is another method that we can take it's not really a different method, but you might not think to do it when it comes to figuring out what your a, b, and or so on and so forth are in a given problem. So in this case here, I'm going to walk through the two methods again, and then this like quote-unquote third method. So the first method that we talked about in one of the first or second videos was to plug in nice values of x, convenient values. So plug in nice x values. So for instance, we could plug in x equals 1. If we plug in x equals 1, we have 1 minus 2 minus 1, which is just negative 2 for the left-hand side. And we plug in 1, we do get this entire bx plus c term canceling out, and then we're left over with 2a. So immediately and very quickly, we determine that a is negative 1. Not bad. Now, here's where we run into a little bit of an issue. If you want to plug in something to try to cancel this term, can't do it. Now that's not entirely true. That's where the third method comes in, because we can plug in I or negative I, complex numbers. We can do that. But for now, let's just keep it real and just say, hey, I can't plug in anything to cancel this term. So instead, you can do what we've done in the previous video, is if you've exhausted choices, you can just plug in another sufficiently nice value of x. Like you could plug in 4,000, but let's just plug in 0. It's a little bit nicer to work with. So if we plug in x equals 0, then the left-hand side collapses to negative 1. The right-hand side would collapse into a plus c times negative 1. So we actually have minus c. Furthermore, we know a is negative 1, so I can replace a with negative 1. So the negative 1's cancel, and we're left with 0 equals negative c. Well, that's only possible if c is 0. There we go. So we were able to get c fairly easily as well, even though plugging in x equals 0 didn't actually quickly and entirely eliminate one of the terms. That's okay. So we know a, we know c, we just don't know b. So what we could do is plug in another sufficiently nice value for x. So we could just try -1. So if we plug in -1, the left-hand side will be 1 plus 2 minus 1, so +2. I'm going to replace in the values of a and c when I do this. So here, a is -1, so we will have -1 times 1 plus 1, so 2. So -2, plus, this would be -b plus c, but c is 0, so -b, and then here we'd have -1. So adding 2 to each side, multiplying the negative b by -1, so we get b equals 4. So that gives us everything we need right there. Okay? So maybe I'll call this method here, actually method 2. Let's come all the way up here, since I'm definitely gonna run out of room. Oops. For method 2, we talked about multiplying it, meaning this equation, these terms, where applicable, multiplying it all out, / equating coefficients. So maybe instead of slash, I'll say multiplying it all out and then equating coefficients. So the left-hand side's already all multiplied out, so we're good. Here we can have ax squared plus a. Foiling this last term, we would have bx squared minus bx plus cx minus c. Then we want to collect our quadratic factors, our terms. So we've got an ax squared, we've got a bx squared. So we've got that. Plus all of the things in front of an x, which would be a -b plus c. And then all of our constants. So this would be a minus c. And again, you want to equate the coefficients. So whatever's in front of x squared on the left is a 1. So this coefficient must equal this coefficient. So equating coefficients allows us to say 1 must equal a plus b. -2 must equal c minus b. And lastly, -1 must equal a minus c. Okay? So what I can do here is I can take these two equations and add them together. If I add them together, I will have -1 equals a plus c, because the b's will cancel. Then I can add this equation to this equation, which would give me -2 equals 2a, but the c's cancel. So then we have a equals -1, which matches what we already found a different way. Okay? Not only that, but since I know this equation, if I know a is -1, this forces, if we plug this into, if we substitute this in, that will yield this answer, which is c equals 0, because the -1s will cancel and we'll be left over with c equals 0. Lastly, we can take this equation here and we can sub in a and c. Well, there's no a in this, so I guess just sub in C. And this will give us -2 equals -b, which implies that b equals +2. All right, now notice here, interesting, there is a discrepancy. So let's double check our work. This is a great opportunity to double check our work. So we got everything else correct here. Let's see here. So it looks like our mistake was when we were substituting in -1 into this term right here. -1 minus 1 is -2. We have this as -1, so this should be a -2. So let's just change that really quickly to a -2. So then this gives us the equation. We add 2 to each side. So we still get that 4, but then here we have 2b, which implies that b is equal to 2. There we go. Okay. So that's one way to do it. Or actually, it's two ways to do it, let's say. The third way that we can do this is very similar to this example here. We can essentially just plug in complex numbers. So maybe I'll call this method 1.5. Or even better, I'll call this method I, since it's very similar to 1, but we'll take a look at the complex version of 1. This is method I, let's say. In this method, it's same as method 1, but allow for complex numbers to be used. So let's just go ahead and pretend we plugged in our nice value of -1. Right? So we plugged in -1 and we got this to cancel out. And even plugging in 0, that yielded good results. So let's kind of pick up right at this stage, okay? So let's just say we already have found out that A is -1 and C is 0. What we could do now is plug in x equals I. So if we plug in x equals I, then the left-hand side of our equation becomes -1 minus 2i minus 1, and that would equal, let's see here, we already know a is -1, but plugging in I will cancel this whole term because I is a root of this polynomial. So this term goes to 0, and we just have to plug in I to that second term. So this would be bi plus 0, since c is 0, and then we would have I minus 1. Do the same thing. We'll factor things out and simplify. So this is -2 minus 2i. And if we distribute the bi, we have bi squared minus bi, which is -b minus bi. So we got -2, -2i. And even if we equate coefficients here, the real part, they need to be equal. So this right here gives us -2 equals -b, so b equals +2. And if we equate the complex coefficients, so the coefficients on I, that implies -2 must equal -b, so b equals 2 just as well. So don't be afraid to plug in complex numbers. It works nicely as well. All right. So let's make some room here. We have all of our values. So let's erase this one up here. So we know that this is going to be the integral of negative 1 over x minus 1 dx. And then here we have 2x plus the integral of 2x over x squared plus 1 dx. So this becomes negative natural log absolute x minus 1, and this is a u sub. This is a u sub. This would end up being the natural log absolute x squared plus 1 plus c. You would let u equal x squared plus 1, so du is 2x dx. We have a 2x dx, so that immediately becomes a du, and we have 1 over u du, so natural log absolute u, and then back substitute to give us that. Again, we can simplify this because we've got logs x squared plus 1 over x minus 1 plus c.